Here's a scholarship board in my school, and if we look here, you can see an individual who was awarded a scholarship in 1936 called G.J. Skelt, a cloth workers scholarship at the Royal College of Science in London. Well, while rummaging through some old stuff from a cupboard, I happened upon these lab books from G.J. Skelt from 1937, November, January, and, well, this is January 1937. So these first two lab books were from the first year that they were in that college, that institution, that university. So they started the course in 1936. That means they'll have been born in 1918 or thereabouts, maybe 1919. Although I don't know whether they start that course at 16 or 18. There's been changes to the education system since then. But let's say 1918. That means that they would be 106 years old at the moment. So the likelihood of them still being around is quite low. But it'd be nice if they were. We could reunite this individual, G.J. Skelt, with their lab books. I assume the G stands for George, but I don't know, there's no indication. We do know something that happened to him. I did some research on the computer, and what did I find? Well, this here is the handbook, the Leon Sea Sailing Club handbook from 1940. And someone had had the good sense, or the good thought to scan this in. So this was found on the Lee Sailing Club website. Just scroll up a bit. You can see the URL there. It's found on the Lee Sailing Club website, in their old archive. And what have we got in here? Well, we've got the lady members list. Very different time. Dates and times when they'll be able to go sailing and racing. Sweepstake races would be held on above dates if entries and other circumstances permit. Further details will be posted on notice board as soon as possible. We're not interested in that. If we scroll down far enough, Cup winners from the previous season from 1939. So this must be from 1940. It does say it's from 1940. If we scroll down, it has a list of who owns what boats. And here we have a boat owned by G.J. Skelt, an Orks cutter called Sabrina. And it's probably the same G.J. Skelt. So it sort of matches up. So 1940, they were still around, probably 1936 to 7, 37 to 38, 39 to 40. So they were probably just finishing off their course that they got their scholarship for. But they still had this boat down in Lee, an Orks cutter, which, I mean, this is, if I Google Orks cutter, it's going to be something like this with a gaff rig, quite a large boat. 1937, so this is the right era. Big old boat like that they had. What else do we know about G.J. Skelt? Well, they joined the military. We know they joined the military because we found this. This is from the Gazette, the London Gazette, and this is a very old archive thing that's been scanned from 1947. So we skip forward more than 10 years. We skip forward to the other side of the Second World War. And what do we discover? Well, Corps of Royal Engineers. And on that column, the Corps of Royal Engineers, we find G.J. Skelt. There he is. War Subs Lieutenant G.J. Skelt. We've got his number here, 253376. Relinquishes his command on the 3rd of December 1947 and is granted the honorary rank of captain. Well, what happened to him then if he relinquished his command? Let's zoom in a bit. Might be easier to see. G.J. Skelt there, War Subs and his number. So he relinquishes his command. So what? What happens to him? Well, it's difficult to say, but here we've got a document and you can see that he is listed as the Assistant Director for Development, Mr. G.J. Skelt, BSc, bunch of letters after his name, acting. He's the acting assistant director in 1963. So he's got some sort of senior post there. His name appears in a few places in this document. He's listed as the chief engineer in the development office for 1962, so he obviously got a promotion from chief engineer. And here he is as a report from when he was chief engineer. Might be interesting for you to read, not sure. It's quite dry stuff. This document, let's just go right to the start. There's a few, let's just go backwards through the references to G.J. 𝗟𝗀, might as well. So if I scroll backwards, chief engineer, development office, I think they're just the same references. Mr. G.J. 𝗟𝗀, chief engineer, carried out duties of senior posts. You know, he also did a senior role, there he is, chief engineer. And if I go right to the very beginning of the document, we'll have a look and see what the document is. The Annual Departmental Reports, 1954 to 1955, from Hong Kong. So after leaving the military, the engineering corps, he must have been stationed at some point in Hong Kong, I assume, I don't know, but he decided to stay there in Hong Kong, and which was part of the Commonwealth at the time. So he decided to stay there in Hong Kong and work on. Here we've got another report. This one's from 1967, so we skip forward again. Let's see how G.J. 𝗟𝗀 is getting on here. So, how do I find G.J. 𝗟𝗀? Results. Well, where is he? It's all the way down here. Let's click on that. Bang, there he is. So, here we've got the Port Executive Committee. And so G.J. 𝗟𝗀, back then, he was on the executive committee, the committees and working parties. I acknowledge with thanks the assistance given by members of the following advisory committees during the past year. And he was there. He replaced somebody called Mr. J. Alexander as the government civil engineer. So he was the government civil engineer until he was replaced by J.R. Whittaker during his absence. And I don't know why he was absent. So let's look at another document. It's a rather fancy-looking document from the University of California. I can't read what that bit underneath it says. Foreign and Commonwealth Office Yearbook for 1970. So we skipped forward. How is G.J. 𝗟𝗀 getting on in 1970? Her Majesty's Stationery Office, University of California, Davis. That's what that bit underneath said. Right, so let's see how 𝗟𝗀 is getting on. As we scroll forward, 𝗟𝗀 is now the Director of Engineering and Engineering Development. So promotion, they're now the Director. They were the assistant, the acting assistant director. Now they're the director. They've got that promotion. So well done to them. Well done to him. And then if I look, this is an obscure Wikipedia article from the Chinese Wikipedia site. You can see that from the URL. The Electrical and Mechanical Services Department, date of establishment 1948. I don't know whether he was there from 1948 or whether he was, well, we know he stayed in Hong Kong for some time. But if I scroll right to the bottom, near the bottom, there's a list of chiefs. And there he is, G.J. 𝗟𝗀, 1969 to 1971, a chief in the Electrical and Mechanical Services Department, which is part of the Public Works Department. The department was the Electrical and Mechanical Office. So it's all the same person. So that is the Director of Engineering Development. So he was the Director of Engineering Development. Very good. And, you know, that was years ago now, 1971. Let's just have a look at it, work out how long ago that was. 1971, I'm typing it into a calculator because I can't be bothered working it out. 53 years ago. So that would have been when he was 53 years old. And did he retire at 53? Did he carry on in that position? We don't know. The trail goes cold here, and I don't know what happened to him. He may have died. I don't know. But let's have a look at his lab books. So the director was, at one point, a student at the school I teach at and was awarded a scholarship. And he went to, I can't remember what it said, but we'll have a look in a second. It'll be in here somewhere. So January 1937, on the subject of heat engines. Let's start with this. So, this is February 1937. Didn't do any lab work in the first month. We've got this diagram, and this says, there's a line through it, no, and it says V, different, very different. So this obviously was not good enough, this work, of whatever it is. Looks like some care has gone into it. There's no labels, very different. I think that's what that says. Then we've got the boiler trial. The coal was loaded from the bunkers into a weighed barrow and something onto a weighbridge. There was a small bunker conveniently placed to adjust the load to the required value. The coal was then tipped by the furnace, ready for firing at the time and the time taken. I'm not sure what that means. The coal was fired as required, being fed onto the grate, where even the fire appeared to be thinning, or whenever the fire appeared to be thinning, if holes in the fire are allowed to develop, the current of air through them would carry particles of, I'm not sure what that says, unburned fuel into the chimney. This would seriously impair the efficiency of the furnace. The coal was fired as far as possible at a uniform size without dust. After the trial, the ashes under the fire were raked out and weighed. Okay, so that looks like it's the experiment, and part 2 is feed water. There's a lot of description here. This diagram obviously is a bit better, the feed water diagram, big tick. Yes, we like that diagram. And there should be a high enough resolution that if you want to read anything here, you can just pause it and read it. I'm not going to spend absolutely ages reading every single word because there's 3 lab books here. But I just want you to look at how beautiful these diagrams are. Little tick again. Flue gas analysis. So the flue gases are analyzed for CO2, oxygen, and nitrogen by difference. The flue gas is drawn into a 100 cc pipette B. There it is, that's the 100 cc pipette. By lowering the bottle A. Okay, so you lower this bottle, that's going to draw, because at the moment you're going to have the water levels level. As you lower this down, it draws our gas in. Tap 1 being open. Tap 1 is open to draw the gases in, so tap 1 is over here. 2, 3, and 4 being closed. Okay, fine. Okay, so this is describing how we can do this analysis with these apparatus. Orifice recorder. Tick. Yeah, we're happy with the orifice recorder. Dryness, miscellaneous readings. Beautiful diagrams. So the diagrams can't be faulted. I haven't really seen tables of results yet, I don't think. But we have seen, CO2 is 22, nitrogen's 14. So we've got some sort of atomic or molecular mass here. But no tables of data. Here they are, tables of data. Under calculations, the volumetric analysis of the flue gases gave these percentages by volume. Thus, the analysis of the flue gas by weight is this. So we've All these, of course, would be calculated using slide rules and being done by hand. There's a blue tick there. I don't know if that's just the person marking it ran out of red pencil. I'm just going to keep looking through this, see if there's anything interesting. You know, if Q is a dryness factor of main steam, pressure is that, then blah, 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 blah. Blue tick and a red tick. Well, so whoever's doing the red ticks is still around. Maybe that's peer review with blue, or self-marking with blue, and then marked by red by the teacher. No different to what we do now, actually, if that's the case. Or maybe that should be green. No different to what we do now, but all the answers are clearly laid out. The mathematics is clear, easy to follow. Hello, what's this? Oh, that's beautiful. So, Imperial College of Science and Technology, City and Guilds Engineering College, Department of Mechanical Engineering and Motive Power. That's where this person was doing these labs. They've written down all the numbers they needed to write on this sheet from the apparatus. So a crib sheet they can fill in. Method of stoking by hand, production of draft, natural, type Babcock and Williams water tube. Calculation of this? Something missing there, isn't there? They don't agree with these numbers. They reckon that should be a 2 down at the bottom here. So we still do something similar even now, where we give them students scaffolding, a little bit of support. Oh, empty page. Right, we've got an empty page because we're going to start a new lab here. So simple steam engine. This is their first year of this course, so the 8th of March, we're getting towards the end of the first year. It's a diagram of a simple steam engine, beautifully drawn yet again. So, procedure. Let's start from the beginning, the object. So the object of the trial is to determine the efficiencies of a simple, double-acting vertical steam engine as shown in the sketch. Procedure. Readings were taken at intervals of 5 minutes of steam chest pressure. Okay. The weight of condensate, the condenser pressure, the initial and final temperatures of the cooling water, and the head over the orifice in the measuring tank. The spring balance something indicator cards were taken continuously. The condensate, having passed through the condenser, discharged into the tank, where it could be weighed. The cooling water passed into the measuring tank with an orifice through which the water discharged. Gauge, not sure what that squiggle is. Gauge was fitted outside the tank to measure the head of water above the orifice. They said the word orifice far too many times. The discharge was then calculated from the formula, and then we've got this small formula here, units pounds per minute as a mass flow rate by the looks of it, where H is the head in feet. They're not happy with that, not sure what that says. The indicator, which? It says which indicator? So a little bit vague. It was old Skelt there. I'm not going to read all of this. You can read that yourself. The handwriting isn't terrible. It's a little bit different to modern handwriting, but not terrible. On the diagram, we're going with printed capitals to make it clearer. But you're going to want to do that in your handwriting because your hand will get tired. So 4.32 horsepower, BHP, British something, can't remember what that is. Since the engine was of double acting type, there were 2 indicators on each side of the piston. Some data there. It's interesting. 1930s, and we've got degrees Celsius as the unit of temperature. They could do it in the 1930s. Why are there still some people, even now, that want summer temperatures given in degrees Fahrenheit? I will never know. That's a little bit weak. If that's a graph, the axes aren't labelled. I think that's supposed to be a graph, but that's a bit weak. That would not pass competency 5A. I mean, look, that line isn't even drawn straight. A little bit weak. But who am I to comment? They became a director. Oh, another experiments sheet to fill in. Oh, this is big. This has probably not been opened for many decades. So, report on trials of simple steam engine. You just fill in the gaps. Just fill in the gaps. It's quite haunting to think that the individual who did this, 𝗟𝗶, is in all likelihood dead. Oh, look at that. That is beautiful. So this is a compound steam engine, not a simple steam engine anymore. They've really taken some care to draw that, to colour in the different parts. Absolutely splendid. Handwriting has taken a bit of a hit here, but we can read it. The object of the trial was to determine the efficiencies of the compound steam engine. The rated power was 50 horsepower. Both cylinders were jacketed with live something steam. Not sure what that says. The procedure was similar to that for the simple engine. Readings were taken every 5 minutes of main steam pressure, receiver pressure, condenser pressure, jacket pressure, inlet and outlet temperature of cooling water, quantity of cooling water, head over orifice, head in condensate measuring tank, temperature of hot well, receiver drainage was weighed every 20 minutes, and indicator cards were taken every 5 minutes, and revolutions and spring balance. The receiver is placed between the high and low pressure cylinder for the purpose of extracting the condensed steam from the live steam before entering the LP, the low pressure cylinder. This is a necessary precaution, for the pressure in a low pressure cylinder is, except right at the beginning of the stroke, below atmospheric. Thus, water cannot be blown out in an accumulation behind the piston, might force the cylinder head off. The drainage from this then consists of steam which passes through the high pressure cylinder but not the low pressure side. It is measured directly by weighing. Really detailed. You could probably follow this yourself to see exactly what needed to be done. And I just want to look at every page. There's so much in this. This technology is obsolete, I suppose, but is it? The principles are all here. The principles of mechanical engineering are all here. Experimental compound engine. Again, we're filling in all the gaps. This is still the heat engines book. Have we reached the end? Oh, it looks like we've reached the end of the heat engines book. And there we have it. At the bottom there is stamp, 30th of May, 1937, stamped and signed, City of Guilds Engineering College, Mechanical Engineering Laboratory. So they look like they've stamped the last page of students' work. And then that book's done. Then we've got materials. And we've got materials from January, materials from November. So we can see progression. Well, hopefully we can see progression in the work here. So materials in January. First year, still first year. Diagram is really stepped up a notch in terms of how gorgeously it's drawn. Tension test within the elastic limit. Okay, so this is pretty standard then. Detail of clamp, there's some clamp drawn there. That's an attempt at 3 dimension, I think, but it's No, it's not terrible. It's got an awkward shape to draw, I suppose, but it's not quite there. I think we lose something nowadays with using computers. We lose the ability to draw diagrams. This is nice, look, descending in red. So ascending in black, descending in red. So we can tell we're still within the elastic limit, which is what we were told. Data, would this pass competency 4? Well, microscale and then thousandths. That means thousandths of an inch. So that's a unit. Strain doesn't have a unit. Pounds per square inch, pounds. So it's got units on here. So I think that would probably be okay for competency 4. Although if we look here, we've got sometimes where the numbers have different numbers of decimal points on a scale reading. That's not ideal. You really ought to be recording these numbers with the same number of decimal points. It indicates the resolution of your recording instrument. So actually they might fail competency 4 for that. Competency 4 as part of our A-level practical endorsement. That's, depending how long this video is on YouTube for, the course will probably change soon, and that'll all change as well. But at the moment, that's how practicals are assessed for A-level physics in England and Wales. Bending test on timber. So there's our beam, telescope, so you can see how much something's deflected by, and then we just bend it. Well, that's easy enough. Procedure, the beam was measured. I mean the length of the beam was measured, or the position of the middle of the beam is measured, it's not clear. The safe load determined, the support were placed, the connect distance apart, or placed the correct distance apart, locked, and the beam placed over them. The load was then increased in about 10 equal increments, and the deflection noted by the telescope, ascending and descending values of the deflection were taken. This is a standard practical, this, but the units are interesting because we're using units of load in tons. And here we have it. So W, which is what our load is, it says that on the table, load W, load in tons, extensometer in inches. So that's fine, ascending and descending, quick diagram of what's going on. Change in M in the X direction divided by change in W. They've done a calculation there. Oh, we actually got some calculus. Look at calculus, nothing changes. The total energy in the beam is that. So the energy is going to be the work done is going to be the sum of the force times the displacement. So mass squared over, what's the E? Should we see if we can figure out what EL or E1 is? Or EI? Extensometer in inches? Maybe that's what the E is. Not entirely sure. Not even sure I know what M is. Bending moment of a distance. Oh, okay. Bending moment is mx. The strain energy contained in the length dx is that. Okay. I'll have to take your word for it because I'm not sure what your symbols mean. Okay. Load W in tons, deflection in inches. Another graph that's well drawn. Although 0.2, 0.25, 0.3. So this should be 0.20, 0.25, 0.30. Or, notice we've got a false origin, 0.175, so that should be 0.200, 0.250, 0.300. We should really have the same number of decimal places along those scales. Summary. The discrepancy between the two values amounts to some 14%. Crikey. However, as the wood is of variable composition, and as each set of values in itself consistent, it seems that the difference is due to differences in the strength of different parts of the beam. Since the maximum stress occurs in different parts of the two experiments, since the experiment, so start with a capital S. Excuse me. The value of E for such wood is known to be about 700 tons. Divided by, what is going on there? So that the mean value is quite reasonable. Actually, the strength of the specimen of timber depends on the point of the, okay. Blank page, torsion test on mild steel. So you've got notches in there so you can twist this around. Picture of the apparatus. Absolutely gorgeous though. Gorgeous work. Oh dear, we weren't happy with that unit. Right down the bottom there. The result is slightly less than might have been expected. However, it was noticed that the test piece had been overstrained several times, which presumably had been axial, were definitely helical, and some difficulty was experienced in introducing the piece into the machine. It will be noticed that the descending values are all slightly lower than the ascending ones, as if the elastic limit had been passed. Yes, yeah, most of them are below there. That's a good observation. Yeah. But they haven't labeled that red is descending. They're just assuming the same convention we had last time. Strut test. This is March the 1st. Diagrams have really taken a step up again. Gorgeous diagrams yet again. Knife edges, screen with scale. You can see everything on there. Procedure. Which are ascending values? Yeah, because look, we've gone green and black. We've changed the convention, and it's not clear what's what anymore. This just says micrometer. This says deflection in inches. That just says micrometer. I don't know what's on the y-axis here. Presumably it's a strain, because you've got micrometer, which is just labeled as micrometer. I don't know what that is. I would assume it's distance divided by distance, so it's going to be some sort of strain, but that doesn't make any sense, because then it would be the same on one of the axes. Micrometer. I don't know what that is. It hasn't been picked up on. Micrometer equals load. Right, okay. So obviously they're measuring something to do with the load, but they're measuring it calibrated against a micrometer. Right, so this is load versus deflection. This is Hooke's law, just Hooke's law in more detail. So someone's lunch is in there. Oh, that must be the end. 30th of May, 1937. Mechanical Engineering Laboratory, City and Guilds Engineering College. But there's more. No, there's more, look. Attention test to destruction. Yes. Oh, hello. What's happened here? Looks like someone's accidentally glued something, and I'm not going to be able to open that. Looks like someone, maybe the same student in the past, has tried to and has ripped it in doing so. So I won't touch that anymore because there might be something in that. This has been stuck over. A Rishley testing machine fitted with autographic recorder. Oh. Gauge length. I can look at this all day long. Look at this. Hardness test, Irwin and Britnell tests. So, test piece, a tool. We're going to push into it with a vernier to see how far it depresses. All the units are in inches, which makes sense. Table the results there. It looks like it's been stuck over. Naughty, naughty. Don't want to do that in a lab book. Whoa, look at this. We've got data sheet 15, logarithmic. Stuck in a logarithmic scale for all of us to enjoy. You had to buy a separate logarithmic scale so they could draw it and get a straight line. That is great. God, you think to yourself, I don't want to look at any more of these. because I've been looking for ages, and then you just keep finding interesting things. Comparing steel and brass. The disadvantage of whoever's test that is that the cutting edge of the tool is something to become blunt, liable to become blunt, which will substantially alter the readings. This disadvantage is overcome in this test by using, in the other test, Brindle's test, by using a ball as indenting tool, as this shape is less liable to becoming worn or deformed. However, in this test, the hardness becomes dependent on the load applied, so that the standard conditions of loading are essential. Hardness, impact, and Vickers diamond test. I think they still do this in geology even now. So if you're studying geology, you might find this bit really interesting. Teeny tiny graphs, not good enough. That would fail competency 5A. Graph is not big enough. Principle. Difference? Not sure what that says. Diagram? Diagram of Vickers hardness machine, not the principle. Yep, they've got the screw back to front. If you rotate this screw, so you look down this side and you rotate it clockwise, that would actually tighten, and you rotate it anti-clockwise, that would loosen. So that's right. I don't know why that says left hand. That's right. Oh, no, it's not. It's the other way around. Look, the way the thread is. If I rotate it clockwise, the screw loosens up. There's real attention to detail when marking this. Real attention to detail. It's just data after data after data, compression tests. Really interesting. Timber bending test. I mean, I can't watch this. I can't do this too long because no one's going to want to watch it. Heading? No heading. Pounds, inches. Don't know what that means. Where are the headings? Stamped 24th of January 1938. And then we have the one for materials. Another one for materials. This immediately follows from it. Here we go. So loading, limit of proportionality, and then failed, and failed, and then failed. Failed 3 times. 3 failures. There's the beam, and he's sketched where the failures were, the cracks in it. The fractures. Timber compression tests. Diagrams. Mathematics. Headings? Where are the headings? Still not drawing headings. You're not learning. Compression tests. The school bell's going to go in a minute, so I should probably stop looking at these. But yeah, this individual had a very, very successful career. And it's so wonderful to get a little glimpse at their life before that successful career, the work they were doing, the attention to detail. They deserve to have a successful career because of their attention to detail. Another left-hand screw. Whoops. Maybe it was left-handed. There's your I-beam. We've got so much good stuff in here. So much good stuff. I could spend hours just looking through this. Spring compression test. More data. Loading and unloading. The unloading looks really shaky there. I don't know what's going on with that. Looks really, really dodgy. Fatigue tests. Oh, look. The attention to detail. Every part labeled. Beautiful. Oh, just beautiful work. That That klaxon means it's the end of the lesson, so I need to go and teach some year 12s, but here we go. Look at that. They've actually printed some results. 24th of January, 1938. And that's the end of that. So, if you know G.J. Scheldt or his family, I imagine they're all in Hong Kong. He spent a long time in Hong Kong, it seems. Get in touch. Let me know. I'll put these in the school museum for now, but I think they belong to him. Maybe they were donated to the department before I got here. I've been at this school for a long time, but it could have happened. I hope you found that as interesting as I did.